This video is going to be over energy diagrams and quantum numbers. This is a video you'll probably want to view a couple of times until you get the hang of what those quantum numbers actually mean and where they go. So before we can actually start talking about this, we're going to go all the way back to Bohr's atom. So Niels Bohr, we talked about some things that he proposed in a different video, but he ended up studying the emission spectrum of hydrogen to determine that electrons are in different energy levels, and he also tells us that every element has a unique emission absorption spectrum. Now, he did a lot of other things. I'm just going to kind of run through this. You can read this for yourself. But the big parts of it is that he determined that electrons possess a fixed amount of energy. And furthermore, we've talked about electron clouds a little bit. At this point. We know that those electron clouds are made up of energy levels that are like the rungs of the ladder. I'll show you what those actually look like in the next slide. But the amount of energy that's possessed by an electron determines its energy level. I don't want to read this whole thing. There's got to be a better way to do this. Okay, let's start over. Just delete that first part and run through this whole slide again. So here are some other things that Bohr figured out. Now you can read this for yourself. I'm just going to point out the main parts of it. But Bohr tells us that electrons possess a certain fixed amount of energy, and that energy is retained in those electron clouds that we've talked about. And inside those electron clouds, you have different energy levels that are like different rungs of the ladder. And I'll show you what we mean by that in just a bit. But in those levels get farther and farther away from the nucleus. And as they get farther away from the nucleus, they get higher and higher energies. That's what I want you to get from that paragraph. In order to move from a lower energy level to a higher energy level, you must gain an exact amount of energy, and that's known as a quantum. That's where we get those quantum numbers from. So the electron is going to be found in two different states. It can either be in the ground state, which is kind of where it just kind of likes to chill at, where it sits when it's resting. And that can also be in an excited state, and that's when it's gained some kind of quantum energy and has jumped from that ground state up energy levels. That's the excited state, and that's when it's free to do all kinds of things. Now he also talks about two different spectra. You have an emission spectra, where light's being emitted, and an absorption spectra, where the electrons are actually going to absorb the light. And what I want you to get from this is that light's going to be emitted as electrons fall to lower energy levels. So as the electrons go from excited back to ground state, it's going to emit light. On the other hand, light's going to be absorbed by electrons as they move to higher energy levels. So it's going to suck in light as it jumps up from energy level to energy level. And here's those energy levels, what we mean like it's rungs of a ladder. You have your first energy level down here, N. I'll show you what N means in just a bit. But that's going to be your ground state. That's where you're hanging out. In order to move up the energy levels, you're going to have to gain energy. And then here's your processes down there. Light's going to be absorbed. You're going to have excitation as you jump up from the first energy level through 2, 3, 4, and 5. Now, once you're in the excited state, like this cheerleader over here, you're eventually going to come back down to your ground state. And as you're coming back from excited state to ground state, you're going to you're going to lose energy, and you're going to emit light. So in case you ever come across Schrodinger, they play a lot with him and what he did in Big Bang Theory. But the big part about Schrodinger is that he agrees with Bohr about certain things. For instance, he agrees with Bohr about energy levels, but he doesn't think there's an exact path. But he does describe a region with high probability, and we still call that an orbital. So they're the same but different, not a big deal. But here are your four quantum numbers, N, L, ML, and MS. We're going to go through each one of those four quantum numbers. You're going to need to tell me what they mean and what they look like. And in these numbers, there's a whole bunch of analogies we can use. A good one is like an address. N is going to be your state, L is going to be your city, ML is your street, and MS is your house number. Each one's giving you a little bit more information. Another good analogy is like a ticket. It tells you what section you're in, what row, what seat, and what stadium. Let's start at the beginning. N, and it's normally going to be a lowercase n. N is going to be the energy level. It's the principal quantum number. You saw that when we were talking about the rungs. But the higher value of N, the further away from the nucleus it is, and therefore the higher the energy level. Because it's being farther and farther away from the nucleus, it's going to be at a higher energy level. And this thing right here, you're going to need to memorize it, because the number of electrons is equal to 2 times the energy level squared. So if we take this, we're going to go all the way through our 7th energy level. But if we start at N1, the equation is number of electrons, I'll put it up here, number of electrons equals 2n squared. So you'd have to plug this in. Remember, you've got to follow your order of operations, square your n before you double it. So it's going to be 1 squared equals 1, then 1 times 2 equals 2. So you're going to have 2 electrons in the first energy level. That would be like a helium atom. Then N2, you're going to square 2, and that equals 4, and then you're going to double that, and that equals 8. So you have 8 electrons in the second energy level. And you can keep on going. 3 squared equals 9, times 2 equals 18. 4 squared equals 16, times 2 equals 32. 5 squared equals 25, times 2 equals 50. 6 squared equals 36, times 2 equals 12, 72. 7 squared equals 49, times 2 equals 84. So you can see as we jump from energy level to energy level, we're definitely getting a lot more electrons involved in this process. Now sublevels is going to be the second quantum number. It's represented by the F. So each one of those energy levels we just talked about is divided into specific sublevels, and those are regions of space that have a very specific shape. We can only really define 2 of those shapes. The other ones that get kind of weird. But each one of these sublevels, or just like our energy levels had different amount of energies, these sublevels within those energy levels also have different amount of energies as well. So here are sublevels S, P, D, and F. And we'll see those on the periodic table. We'll point those out. But they're in increasing order of energy. So S is the lowest energy, F is the greatest energy. So if we're working with energy levels, we're only going to do 4 energy levels here because we're only going to work with S, P, D, and F. As you increase energy levels, you're going to increase sublevels. So at our first energy level, the only sublevel that's going to be present is S. We're going to go to the second energy level, so we're going to add a sublevel. So now we're going to have S and P. And again, with the third energy level, now we have S, P, and D. And then fourth sublevel, we're going to have S, P, D, and F. Okay, the third quantum number is the magnetic quantum number. It looks more like this. Oops. This actually looks more like M with a subscripted L. And these are orbitals, the magnetic quantum number. Each sublevel contains orbitals which are regions of high probability for finding electrons. Each sublevel contains orbitals which are regions of high probabilities for finding electrons. This number indicates the orientation of those orbitals. Each orbital can only have 2 electrons. Okay, so what this number does is it indicates the orientation of the orbitals we were just talking about. Right? Where do we go with this? I forget. Oh. This number is primarily contained, or this quantum number is primarily concerned with shape. And in that shape, we have to keep in mind that each orbital can only hold on to 2 electrons. So we're actually only predicting an area where some electron might be found about 90% of the time. So here are your shapes. In our sublevel S, we're only going to have 1 orbital. So if we only have 1 orbital, we can only have 2 electrons. And that shape is going to be spherical. I'll show you what these look like in the next slide. The next sublevel up is P. P has 3 orbitals. And by the way, they're going to look like this. We can only have 2 electrons. I'll talk about what those arrows mean in that one. And the P sublevel is going to have 3 orbitals. So it's going to have 1, 2, 3 orbitals. And so if each orbital can have 2 electrons, we can actually have 6 6 electrons. Each one of those arrows indicates an electron. Don't worry about where they're pointing right now. And those look like dumbbells. So this was a sphere. This one will kind of look like a dumbbell. Now D has 5 sublevels. So 1, 2, 3, 4, 5. You can add those arrows in if you want. But we're not going to be concerned with the shape because it's kind of hard to define. It's almost like 2 different dumbbells. And the F sublevel has 7 orbitals. So we do 7 orbitals, and we're not going to be concerned with that well because it's just a crazy structure. And this is what they look like. So you see up here, this is our S orbital. It's a sphere. And see, it can only hold 2 electrons somewhere within the orbital. This next level, this is P. And you see how we have 3 orbitals within that. We have 3 orbitals in that. So we have 3 orbitals within that sublevel. Each one of these orbitals contains 2 electrons somewhere within those orbitals. And then D, we're going to have 5 orbitals within that sublevel. And see, each one of those can have 2 somewhere in that radius. This gets to be why we can't define their shape because it's so crazy. And down here, the same theory goes with F. So this is our last quantum number. It's spin. This is really the reason why you can only have 2 electrons in every orbital. Electrons, they're going to have to spin in different directions in order to counteract the spin of the other one. If we have 2 that are spinning the same direction, they're going to repel each other too much. So you can see that in the picture down here. This one's spinning from right to left, and this one's going from this one's spinning from left to right, this one's spinning from right to left. That actually creates a magnetic field, and you can see that this magnetic field's going this way, this one's coming this way, and so those won't repel each other as much. But that's why we're talking about arrows here. You saw these arrows. Each sublevel is going to have an arrow that goes up and then goes down. This one's going to be plus 1/2, this one's minus 1/2, and that's why I was drawing those arrows earlier. We'll get into more about that in the next video.